Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in. We're looking at similarity, similar figures. So we learned about congruent figures in the previous lesson. Well, similar figures is a similar idea. So when we're talking about two figures being similar, they are the same shape, but not necessarily the same size. So that's what's different between being similar and being congruent. If two shapes are congruent, they are the same size and the same shape. So hopefully it won't blow your mind. If two figures are similar, they're not necessarily congruent. But if they're congruent, then they must be similar. So we're talking about ones like this where you have two triangles. They sort of have the same shape to them, but they're a different size. Clearly, the one on the right is bigger than the one on the left. So they're not congruent, but they can be similar. Now, to be the same shape, they need to have all of the same angles. Okay, so all of the angles were equal. Now, as I showed you in the previous video on congruence, if two triangles, or any two shapes for that matter, have all the same angles, that doesn't mean that they will have the same sides. So we're looking at shapes that have all angles equal. In addition to that, in addition to having all angles equal or pairs of angles equal, similar figures have sides in proportion. So what that basically means is every side in the smaller shape, you multiply it by the same number to get the sides in the larger shape. So for example, this one might be 4, 5, and let's say 3.8. So sides in proportion, they might be, say, double the size of the sides in the smaller shape when I look at the larger figure. So in the larger triangle, if I have, say, 8, 10 and 7.6, each side in the larger figure is double the corresponding side in the smaller figure. In other words, I've multiplied each of the sides in the smaller figure by 2 to get the sides in the larger figure. That's what I mean sides in proportion. So we can test that by checking that side in the larger triangle divided by its corresponding side gives the same number each time we do this. And that's true. 10 over 5 does equal 8 over 4, which does equal 7.6 over 3.8, which is 2. Right? So the number that we've multiplied the sides by in the smaller shape is 2. We call this the scale factor. So what we've basically done is enlarged each of the sides in the smaller shape by a factor of 2. And that's what similar figures are. We've taken a smaller shape and we've enlarged it by a factor of 2 or 3 or whatever in the same direction. So it turns out, for example, that all squares are similar to each other because all squares have 4 angles equal to 90 degrees and all sides are equal. It doesn't actually matter what the side lengths of the square are. Two squares will always be similar. So we know that all the angles are equal. So let's say that the side length of the small square was 3, and let's say that the side length of the larger square was 8. So here all angles are equal, but each side in the larger square divided by its side in its corresponding side in the smaller shape is 8 over 3. So this all must be 8 and these all must be 3. So you can see if I take any side in the larger square, divide it by its corresponding side in the smaller square, I get 8 over 3. And that's what the scale factor is. So 8 over 3 is like 2.6 recurring. So we've enlarged the smaller figure by a factor of 2.6 recurring, okay? So let's have a look at how we can use this to calculate unknown sides and angles. So please pause and copy this down if you need it. So I'm going to tell you that the two shapes below are similar. Okay, so I'm just telling you that. I haven't proved it. I know that all the angles are equal, but to prove it, I need to show that sides are in proportion. But this question's different. I'm not asking you to prove they're similar, I'm telling you they're similar, and we're going to use this to calculate side lengths. So let's say, this side will be 10, this side will be, say, 25. This side, let's say, is 18. I'm going to call this X. Say this side here is about 24, and we'll try and find what that is, okay? So we're going to use the fact that these two shapes are similar to find what X and Y are. So when you're calculating the length of an unknown side using similar figures, first step is you need to find the scale factor. So the scale factor, you just find two corresponding sides that you know the length of. So this side corresponds to this side, and the scale factor is just the side in the larger triangle divided by the side in the smaller triangle. So the scale factor here is 2.5. Now, X and Y we need to do just slightly differently. So if we're finding a side in the larger shape, so that would be for X, we're going to end up timesing by the scale factor. And predictably, if we're finding a side in the smaller figure, we're going to divide by the scale factor. Okay, so always use the scale factor as the larger shape divided by the smaller shape. So I found the scale factor is 2.5. So to find X, X is in the larger one, so I'm going to times by the scale factor. So X would be 18 times 2.5, which gives me 45. So the length of X would be 45. Now I want to find what Y is. It's in the smaller shape, so I take the side in the larger shape, and I don't times, I divide by the scale factor. So that should be divided by 2.5 and should get 9.6. Okay, so it doesn't have to be a whole number. So length of X is 45, length of Y is 9.6. So I've used scale factors to find the lengths of unknown sides. Now to find the lengths of unknown angles is easy because angles come in pairs that are equal. So if I tell you that this angle here was 18 degrees and I said that angle's alpha, well clearly alpha has to be 18 degrees because corresponding angles are equal in similar figures. Remember that the angles inside a quadrilateral add up to 360 degrees, and this is what we have here. So I'll put a few more measurements on. So I've put in a few more measurements, and I want to find what the value of theta is now. So remember, corresponding angles are equal. So if this angle here is 34, this angle must be 34 degrees, and if this angle here is 32, then here we must also have 32 degrees inside there. So because angles in a quadrilateral add to 360, I can find theta easily. I just take 360 and I can subtract 18, 32, and 34. So it's 360 minus 84, which gives us 276. So theta is 276 degrees. How easy was that? Hope you've enjoyed this video. This has been the luckiest maths teacher in the world. Have a great day.